Hi everyone, I am Chen Haoyang, a third-year PhD student at the University of Chicago. Welcome to my channel. Today I will give a mini tutorial on Inference-Time Compute, the new technology being promoted after OpenAI O1 release. The slides can be found on my personal webpage, and welcome to send me comments and questions. This tutorial was first presented on October 24th at U Chicago and TTIC NLP seminar, and later I incorporated some content from the Sasha Rush Simons Institute talk, and in November 28th I also incorporated some more open source community efforts to reproduce OpenAI O1. So hopefully this tutorial is now being more strengthened, and yeah, so let's get started. So before we start, there are a couple of disclaimers about this tutorial. So first one, I am not from OpenAI, so I do not really know how OpenAI O1 is implemented. So take what I said with a grain of salt if you are thinking about reproducing O1. Secondly, for the main purpose of this tutorial, so I want to show some key technologies showcased by the OpenAI O1. This is overall termed as the Inference-Time Compute. And also, I am not saying academia should work hard to reproduce O1. There are different agendas, different research goals that we should pursue, and but studying this inference-time compute perhaps can give us some inspiration for studying our own behaviors or investigating some prompting techniques. Also, it's interesting to think whether a large language model should and how can they have this kind of like slow thinking capabilities or assisted-to thinking. Another disclaimer I want to give is that we shouldn't blindly chase OpenAI, but it's good to know what is happening and widely discussed. And also, I encourage everyone watching my tutorial also check out Sasha Rush's great talk as well. There are more rigorous analysis and detailed speculations on OpenAI O1. The link is given in this slide. So just a warm-up example, I grabbed this example from OpenAI O1 website. This is a decipher example. The first line, the left part is just some composition of some random characters, and the right part, the think step by step, is the deciphered version. It means if you read the content, these characters in the left part, then you can decode it some words to be the English sentence think step by step. So using this first line example, can we learn how to can we decode the example given in the third line? This is even a longer composition of random characters, and how should we decode it? To save everyone's time, I will just give the answer. So we can take average of every two characters, their alphabetical order. We average them, and then we got another new number, and we translate it back by finding the corresponding character. So in this example, let's take a look at the first line. The first two characters is O and Y. The O is the 15th character from A to Z, and Y is the 25th character from A to Z. We take an average of them, and this gives us 20s. And T, the first character in the think step by step, is actually the 20th character from A to Z. So this explains how we can do this decoding, and let's see whether language model can do this. The language model here we refer to OpenAI O1. So with that decipher example in mind, let's take a look at how OpenAI O1 solve this problem. So we are now at the OpenAI O1 interface, choose O1 preview, copy paste this example, and we can notice it undergoes a long, slow thinking process. Like if we click it and we find there are many thoughts happening in OpenAI O1, that this whole process would last for about like 1 minute. So to save everyone's time, let's just skip a bit. After O1 had found out the answer, it would compile the whole thought to be a very clear, organized, step-by-step reasoning, and finally give out the answer. So the final answer is like the strawberry. There are 3 R's in strawberry, very famous example. So if we take a close look at this running process, we may identify some key features for OpenAI O1. So first, we notice that it undergoes a long thinking. The thinking is defined as a token string. This thinking happened before the O1 generated the final answer. So we can see that it thinks for 54 seconds. This is pretty long process. And the second key feature is like it would do this kind of like step-by-step reasoning. So we do see that it follows some task decomposition, the step-by-step decoding process to solve our problem. Also, if we take a look at like what the O1 actually did in these 54 seconds, so we see that there are many repeated self-reflection in the trial and error loops. So first, it tries to decode this string using one way, and then it finds this decipher method doesn't work, and then it did some reflection. Perhaps it should switch to some other decoding method like Kaiser cipher shift, keyboard layout, or combined pairing techniques. Then it tries some other decoding method and it succeeds and it would move forward. So this is like a repeated self-reflection in these trial and error loops. Okay, hopefully through example and through these identified key features, we are now ready to go into our today's tutorial. We will introduce several key technologies here. First, we would introduce how we can enable large language model to think, and how can we enable them to do more reliable, rigorous step-by-step reasoning while the help of this new technology called process reward model. And we would also get to know how can we enable large language model to do self-reflection and backtracking. And finally, we would see there is a new scaling loss that's previously overlooked perhaps by many people. The inference time scaling loss that we can see if we keep investing more power in computational perspective, we would get better performance even if we didn't do any training at the inference time. So let's get to the first part, how we can enable large language model to think. Here is the OpenAI quote from their website. It reads, O1 thinks before it answers. It can produce a long internal chain of thought before responding to the user. So the key word here is the long and chain of thought. And later we would introduce what is the chain of thought prompting, and from a theoretical perspective, why chain of thought added its power to large language models. And because chain of thought datasets is kind of like expensive and requires much human labor to annotate it. So we would also see how we can, using some bootstrapping approach, to create a chain of thought dataset so we can train a very powerful model that can do reliable chain of thought. So let's introduce what is the chain of thought prompting. In this screen, we have 2 columns. The left part is a standard prompting, where we try to ask the language model some arithmetic calculation problems to familiarize with the model with this QA format. We give them some in-context sample, some QA pairs, and then we ask the questions about the apples calculation problem. And unfortunately, the model generated the incorrect answer. The right column showcases the chain of thought prompting. It works by way manually editing some rationale explanation at each example, and the model will learn to follow these formats. It also generates some explanation at the beginning, and finally, it generates the answer. And it turns out, like in this way, the generated answer would be correct much more often. And you can check out this new App 2022 paper. And I would call this chain of thought prompting as like a technique to try to teach the model to think by imitating human reasoning process. Well, you may wonder why this simple tweak on the prompting would add so much power to large language model reasoning. Is there any like theoretical grounding, or like is really solid? So there are a couple of like theoretical works try to verify or try to explain why chain of thought is powered language model. And theoretically saying, it says chain of thought adds recurrence computation back to transformers, extending expressivity of transformer to solve inherently serial problems. This is an important problem class, and this many theory works try to dig deeper in this direction. And as an illustration, like say we have a different complexity class like AC0, TC0. You do not really need to know what they are. They are just some like difficulty representation. And the vanilla transformer is this like pink over here. And if we add the chain of thoughts, it slightly increase its expressivity to this blue over here. And to illustrate what could be some example of the inherently serial problems, like some problems that we can solve if we equip transformer with long chain of thought, they include evaluating some arithmetic expressions, doing some automata simulation, and composing some permutations. All these combined together, we get extended capability for evaluating code and doing math. So we see it performs better on reasoning tasks. But there also exist some problems that transformer, even equipped with chain of thought, cannot solve, like some graph connectivity problem. Like if we provide the language model with this edge representation on a graph, then perhaps it would be challenging for a model to answer any node connectivity problem. And the other problem is like linear programming or linear equalities problem that maybe a transformer would also struggle with. And the in context-free recognition, and also kind of like surprising, the transformer even equipped with chain of thought would also struggle testing whether a number is a prime. For more details, I would refer the audience to the William Mariel's work and many other people's work listed here. Well, so far so good. We have seen the power brought by chain of thought. We have seen like the model can learn to imitate this reasoning process to think. But human cannot really offer that much reasoning for every in-context sample. And we would lose the flexibility if we have to annotate the explanation when a new task comes in. So can we ask the model to help to annotate this in-context sample, so later we can train the model to do reliable chain of thought? This is possible, and this is it's described by Star paper. We will start with some question, say some knowledge question or some arithmetic calculation questions, and we will first ask the language model to generate some rationale, and because we are now preparing some training data sets, we can know whether this answer is correct or not. So if this is correct answer, then we can pseudo-label this rationale to be correct and augment this original data set with this generated rationale. But if unfortunately this answer is incorrect, we would then give the ground truth answer as a hint, re-prompt the model to ask the model to generate a better rationale and answer. And if this time the answer is correct, we would also augment this new rationale to the original data set. After we have collected this many chain of thought data sets, then we can fine-tune the language model to do this. So in most examples we have seen so far, we mainly utilize the final outcome to supervise the model to judge whether the chain of thought is doing great or not. But we very rarely ask whether the generated rationale makes sense, reasonable, faithful or not. And it is very challenging to ask the model to elaborate and plan ahead if we only supervise on the final outcome. And there are also some works demonstrates that even some non-informative rationale can make chain of thought works, in a sense that it can, like some random sentences, if we just pretend it's some chain of thought, it can also improve the model performance on some reasoning task. So unlocking reasoning in inference time only is not robust. So we should provide some procedural supervision to supervise every step, and this can be implemented by using a process reward model or PRM. So far, we have introduced how we can enable larger model to think, and we will move on to see how we can enable larger model to do step-by-step reasoning while process reward model. In this part, because we will provide a more fine-grained supervision for every reasoning step larger model generates, it requires many more efforts to collect the supervision data than the previous chain of thought. There are two ways to collect this fine-grained supervision data. The first one is showcased by OpenAI Let's Verify Step-by-Step paper or PRM 800K paper. They are basically seeking high-quality manual annotation from experts for this stepwise annotation. And the other work is from Matt Shepherd. This work is conducted by multiple universities and DeepSeek, this startup. They are using some heuristic to do automatic annotation by language models. Both ways can provide you with some fine-grained supervision data and train a process reward model. And these parts corresponding to this code from O1, it says, through reinforcement learning, O1 learns to hone its chain of thought and refine strategies it uses. It learns to recognize and correct its mistakes. It learns to break down tricky steps into simpler ones. It learns to try a different approach when the current one isn't working, and so on. So now let's take a look how OpenAI collecting this high-quality fine-grained data for doing stepwise supervision. So let's start with some GPT-4. We do not know what is this version it is. This model undergoes some math training to warm up it a bit in this math reasoning task, and it also OpenAI also did some format following tuning. This is to make sure the generated output will follow some format, so we can split every reasoning steps and also split the final answer out using some pattern matching. And after we have sampled some reasoning trajectories using some mathematical questions, then we will ask a human annotation for annotating this stepwise trajectory. And we will take a look at what is this annotation interface look like. This looks like this way. So we present the human with the math question, we present the ground truth answer, and we split every reasoning steps generated by the language models, and we ask the human to annotate 3 labels, like the positive label, the green one here is saying the current step is correct and reasonable. The neutral label, this black one, this is the ambiguity label. This means this step is not necessarily wrong, but it's potentially subtly misleading, and it might be a poor suggestion. The red unhappy face here means the negative label. This is it is saying like the annotator believes the current step is incorrect or unreasonable. After we have collected the three-way classification annotation from human, then we can do typical classification training over some model. Again, here they use some GPT-4 version where we didn't know what it is. And how do we evaluate this trained process reward model? They take a best of n paradigm. This means we use some generator model with sample n output from this generator, and we will pick up the generation that is called the best under this process reward model. And how did they score every generation, every of n output? So the first, they did this three-way classification on every n generations, and they cast the neutral label to positive label, and for each of these n outputs, we have this positive score, right? So the probability for this output to be positive step, and then they multiply this positive score for all steps to be the overall score of the current generation. Then after we assign scores for each of the outputs, we can sort them and pick up the best one. And here is the reported performance. The origin line means that we, by utilizing this process reward model, we can obtain much better performance, and the trend is still like increasing if we just sample more out solutions per problem. And the blue line is like we only use the ORM. This means we only use the outcome reward model, and this saturated pretty quickly. And this performs worse compared with process reward model. And the gray line is the majority voting result, which didn't use any reward model, and it performs relatively even worse. Yeah. The OpenAI approach to collect human annotated fine-grained stepwise this judgment is relatively expensive and laborious. You may wonder whether we can utilize some heuristic to do automatic data collection, and this is possible, and this is verified by the work Matt Shepherd published in ACL 2024. The basic idea is like we still start from some mathematical questions, some simple arithmetic calculation problems, and then suppose we sample k steps using a chain of thought like generation, and we still obtain these long answers. I would utilize this such a rush demonstration here for explanation. So we now suppose we start with some intermediate step. We would log out and see whether we can obtain some good answer in the end. And this illustrates how they did this automatic annotation. So we start with some intermediate steps, like say S1, and then we log out and k steps ahead and see whether some of them can reach to the good answer. And then we can cast the annotation in two ways. In the soft way that we compute the proportion of obtaining correct answers among all these logouts. In a hard score, so we just concerned about whether any of these outputs would lead us to the correct answer. So this YSE and YHE explains the score utilizing logout as the supervision for the final answer. And after we have obtained this score, we can train the reward model using binary closed entropy. And in this way, the trained process reward model can still perform very well compared with not using the process reward model version. And we can see that from this figure, we can using process reward model to improve a Llama 2 70 billion model to perform even better than early version of GPT-4, and it's very close to the GPT-4 June version. So that is a great step towards the automatic annotation. Okay, so I have finished the first two parts, explaining how to teach the model to think and how to teach the model to do step-by-step reasoning. The next step is we want to know how can we enable large language model to self-reflect and do backtracking. Specifically, we will still start with inference-time only solution. We will introduce about self-reflection prompting. We will introduce some limitation for this inference-time only solutions. And we will discuss about how can we teach language model to self-reflect and backtrack using some training methods, using some reinforcement learning. And this corresponding again to the same code from OpenAI O1, but now we will focus more on this recognize and correct its mistakes parts. And we will see how we can enable transformer learn to try different approach when the current one isn't working. So we will still start with some inference-time only solution. In this slide, we will introduce the reflexive paper published in New IPS 2024. There are three columns in this slide indicating three application scenarios that you would work with language model and use self-reflection prompting. From left to right, it is decision making, programming, and reasoning. And now let's take an example for the first column. So we start with some task instruction. We give this task instruction to the model, and we sample some trajectory from the model to see how they can play with this environment and conduct its task. Now we will do some evaluation, like giving them some feedback on how well they did this task. Like we say, perhaps they are doing some hallucination. And then we will ask the model to do some self-reflection to identify its own mistake. Then based on all this previous trajectory, some evaluation and self-reflection, now we can resample the new trajectory, and hopefully this time the model will get it right. And in this paper, they show it truly works in these three scenarios. And here is an example prompt that they write for self-reflection. So they specify the task instruction in the first one or two sentences. And they also tell the model we will give them the unit test results and previous implementation. Suppose you are a Python writing assistant, and ask the model to refine its own outputs and also specify some prompt format, some output format, so later we can easily pass their output to perform this task. In the literature of self-reflection or self-correction, there are various kind of like prompting that you can use, and there is no such like gold standard prompt that you should use, and you can adapt the prompt to fit your task better. However, this inference-time only solution, the self-reflection prompting, also suffers from some problems. And namely, the biggest problem is that the language model cannot do self-reflection without external feedback. Like they need verifier feedback, they need program compiler feedback, or like if you are playing with language model on some math reasoning task, you may need some calculator feedback. This is evidenced and verified by two independent works shown in this slide. Okay, we have seen the limitation for this inference-time only solution, self-reflection prompting solution. So the next part we will discuss how we can using some training techniques to teach the language model to do reliable or even more powerful self-correction or self-reflection. And before we start, I want to quote this good saying from Q1 Chen when he delivered a talk at the MIT seminar. He said we need to properly incentivize the model to teach them to exhibit some high-level capability to solve problems. My personal interpretation is like we need to properly design the reward in a reinforcement learning paradigm to train the model to exhibit algorithmic capability to solve problems. So this directly points to this Google DeepMind paper, training language model to self-correct while reinforcement learning. I put this one as the footnote of this slide. So what did they do? Try to teach the model to self-correct or self-reflection. So let's review a bit about the standard reinforcement learning. So we maximize the typical final round reward and reusing the great materials from such a large talk. This means we sample multiple trajectories and we only give stabilization signal or reverse signal at the end of a reasoning chain. And this translates to this typical PPO objective. And but this, if we only optimize this objective, we will suffer from two problems. One is a distribution shift. This means the actual mistakes that the model need to correct in the deployment time may deviate from the training example that they see. So I guess this points to some straightforward solution that we need to shift from supervised fine-tuning to some online reinforcement learning approach or some other iterative approach. The other problem is less apparent or is more nuanced. It is called the behavior collapse problem. It is saying like the model, if we teach it, train it using traditional reinforcement learning, it would only learn to produce the best first attempt response plus some superficial edits. What does this mean? So we start with some prompt, we sample some base response, and under typical reinforcement learning, we would only train the model to do some very small edits at each iteration, and it make very slow progress or even no progress towards the final correct answer. And what we want to do is like maybe we still start with the prompt and base response. We want to constrain the base response a bit and try to enlarge or encourage more updates between the second response and the first response. And again, at the same time, we want to encourage the second response to make progress towards the final correct answer. So this is our way to do this. So we modify this scale divergence from xt to x1. This is saying we want to constrain the base response. And then we also reshape the reward at each response and try to make sure we can encourage more edits and make more progress at each step. And this is best explained in the figure in the paper. So we will have two-stage training. The first stage, we will constrain the base model and maximize the reward. And the second stage, we would maximize the shaped per response or per step reward. And more details on how to design this shaped reward is detailed in the paper. But this is not the complete story. So this may be only limited to the two-round response or two-round iterative prompting. Then we want to ask, what about the long backtracking? How can we enable Transformer to do this? There are actually different ways to teach language model to do backtracking. And let's start with something more simple that is called the string of search approach, published in the recent finished Column 2024 conference. What did I do is like, again, I want to thank Searchformer for providing these great materials for teaching. We start with some search tree and we try to linearize it by maybe cast the sibling nodes to some child node or for other nodes. So we somewhat convert this tree structure to be a chain structure or a linear structure. Then we can use the typical next word prediction to train the model. This is a key idea behind the string of search, how we can teach the model to backtrack and do searching. And in this paper, the search tree is defined by the DFS, BFS kind of style for decoding from the language model, and we streamline, make it to be a token string and predict the next token. And this is the example shown in the paper. So they are doing some math calculation question, and they will sample some diverse search tree, and doing some format conversion. We would get this string of search formats. So we will start with some initial states, and we do some search backtracking in the middle. Let's ask the model to predict this backtracking step as the next word prediction, and until we reach the goal state. So this is the string of search. We cast this teaching problem to be next word prediction by reformatting the search tree to be a token string. Of course, BFS, DFS might be less efficient if we want to redeploy this transformer model to do searching task. So we can also seek to other search algorithms like A star, and this point to the Searchformer paper, also published in Colon 2024. So what this algorithm saying is like, so first we introduce some maze navigation task. We start with this green cell, and we want to navigate to this orange cell, and we can follow some trajectories here to get to this target cell. And we still we run this A star algorithm by assigning some heuristic in this maze navigation process, and we can then also convert this A star search tree to be a token string and ask the model to predict the next token. So here we demonstrate how we can convert this A star planning to be a token sequence. And this is the example for how we can convert from search tree produced by A star to token string, and we still perform next word prediction to teach the model to do backtracking. Okay, so I have finished these three most important parts, and I really appreciate that you have watched so far. And now we will talk about the inference time scaling laws. Perhaps more people will get excited about this. So specifically, we'll talk about first introduce some strategies we have discussed so far that have been identified to be scalable, and also we will talk about the underestimate or overlooked inference time scaling power. Like it is a very good complement to the training time scaling laws. And this corresponding to this figure in OpenAI O1 or website, where they say we need to scale jointly the training and inference to make a good model. So let's review a bit about what inference time compute strategies that we have discussed so far. So first, when we introduce about process reward model and its variation, we talk about this best of n paradigm. That means we sample n solutions from some language model, and we select the best one with our verifier or ORM or process reward model, any model. We can also extend a bit, like we can do beam search with a process reward model if you have one. So at each step, we can sample top n steps using our process reward model and keep moving on, keep expanding on these top n samples only. So this is a beam search solution, and we can do it even more in a computational expensive way, like we can do overhead search or MSTS. So at each step of beam search, we will roll out k steps in advance and using the process reward model for this k step rollout to represent the value for the current steps. In some sense, we are doing some look ahead planning for k steps using the process reward model to gauge the potential for expanding the current node. And using this great figure from Sherry Snell's paper about the test time scaling laws, we can understand these three strategies better. The best of it is like we sample n solutions and we only provide the supervision or reward signal at the end, and then we can pick up the best one from this n solution. Beam search is like at each step we will intensively query the process reward model to ask them to help us pick up the top n sample to keep expanding. And look ahead search is like we roll out k steps and to perform an expensive next step. And empirically, Sherry shows in his paper like the beam search achieves a better computation and performance trade-off because look-ahead search is too expensive, but the performance gain is kind of like marginal compared to the beam search. Then we will see this typical or like very standard scaling loss figure, but this time we are discussing this scaling loss in inference time. So there are two columns here. The left one is a self-reflection, self-refinement scaling loss. Anyway, it is a iterative prompting scaling. And the right column is more of about the best of n decoding strategies. So it's more like a parallel sampling. So in both columns, we can see the clear increasing trend when we invest in more computational power, as the x-axis is the generation budget, and the y-axis is the math accuracy. This corresponds perfectly to the testing time scaling plotted in the OpenAI O1 website. And I think maybe if we can scale both the training times and the testing time, the computation, then we can get better and better performance. At least this is the message that O1 want to share with us. So put it together, combining all the message or technology we have discussed so far, let's derive a somewhat a minimum set of assumptions that we can safely assume about OpenAI O1 if you are interested in reproducing O1. So we assume that maybe we only have single language model with coherent chain of thought, or we do not want the model to just simply follow expert example because we will suffer from distribution shift problems. Also, this kind of like self-reflection behavior should be learned, not just get succeed on individual data points. We should teach the model to learn this high-level behavior. And the keywords here are reinforcement learning, chain of thought, and potentially we will need to train the model in a data efficient way. And this points to multiple hypotheses or speculations that potentially implement the OpenAI O1. And again, these materials are from such a rush O1 tutorial, and I would encourage audience to check it a bit. As over the time that I released this video, the open source community and many companies have tried to replicate the success of OpenAI O1. Here I just name a few. So the Q1, the Alibaba company, they developed this QWQ 32 billion preview model, and this is available in Hugging Face. And you can see that performance in this figure is much better than some baseline model. I think it's better than Claude 3.5 and GPT-4o. And the Skywalk also released their 8 billion smaller size O1 replication, also on Hugging Face. There are some academic efforts try to replicate OpenAI O1, and here are some progress reports. And also some Reddit users reported that perhaps through some prompt design, we can make Claude 3.5 sonnets to outperform O1. And here is the link that if you are interested to check a bit. Okay, thanks for watching so far, and here are some final takeaways. So first, I think prompting can be an effective way to discover some emergent desired behaviors like thinking, like self-reflection. Though this inference time only solution is not robust, as I explained before, but my advice would still be playing more with long-term model to see what they can do or what they cannot do. If you would like the language model to master some algorithmic capability like slow thinking, like self-reflection, that can work across tasks, that can work robustly well, we have to properly incentivize the model to learn these nuanced behaviors. Otherwise, they will just overfit some individual data points. These first 2 points kind of reflect my thoughts on organizing this tutorial. So I always start with some inference time only solution, talk about their limitation, and then talk about how we can train the model to do well. I think this is my current rule of thumb to do large language model research and play better as a large language model. Final takeaway is like the inference time scaling previously overlooked unlocks much potential for the model and can be an effective complement to training time scaling. So to build a better model in the future, when you think about jointly scaling the inference time and training time, perhaps following OpenAI. But I am very excited if someone can point out some alternative solutions for that. That is all, and thanks for watching.